cookies and granola bars and a little chocolate.
What kind of cookies? What kind of cookies?
How much extra credit did you give them?
No, it's my Valentine's.
Miss Phillips has a boyfriend.
She's a husband.
Oh my!
Difference.
Whoa, calm down.
Michael, we all know. Remember all those times I gave you chocolate in this period?
No.
That's true. Those like that.
All right, just so you know, we're all recording here. It's already started. This is 15.3, electric force. We're going to talk about Coulomb's law, and we're going to calculate the force between multiple charges. This is probably the hardest part of this section of all of like what we have left for the year. And that's only because you need to remember your vectors. All right, so Charles Coulomb, some dead guy between 1736 and 1806. Wow, it's only like, well, I guess it's
7 years.
That's not bad. All right. I thought it was 40 for a second, and I realized math. It happens. All right. He studied electrostatics and magnetism, and he looked at the strengths between these like magnets and electric charges, and he identified the forces acting on these. So he comes up with Coulomb's law, which is the electric force, Fe. It looks a lot like the gravitational force setup, right? We have Ke, which is kind of like that big G gravitational constant. This is Coulomb's constant. It's a little k, and it's 9 times 10 to the 9. Then it's between two charges, Q1 and Q2, over the distance squared. Now this looks a lot like the gravitational force, where we have a big G and then the two masses over r squared. So very similar setup, but this is for electric force and not gravitational force. What? With charges, and I think we learned this earlier, like charges repel and opposite charges attract. So you have some positive charge and some negative charge. And remember that positive charges are only missing electrons and negative charges have extra electrons. Now your Q's are going to be measured in coulombs, and your distance R is going to be the distance between them, and that's measured in meters. So for Coulomb's law, electric force has the following properties. It's going to be directed on a straight line between the two particles. It will be proportional to the magnitude of the two charges. And it's attractive for opposite charges and repulsive for like charges. Now this is in your book. I think I shortened it a little bit so that it was very straight and to the point. All right, this is in your book, table 15.1. It has the charge of an electron and the charge of a proton. Notice the exact same charge, even though the proton has a lot more mass than the electron. I would memorize it. You're going to use it a lot. 1.6 times 10 to the negative 19 shows up all the time. The mass you'll use, but you won't see it as often as you will the charge. But it's in your book, so. And it's also in the back of your book. It might even be in the front of the book.
Yeah, so this is like something that we should be writing on one of our note cards for tests, right?
Yeah.
Okay. Is this going to be on the reference sheet for the APP?
It is, yes. Okay, so remember that force is a vector. So in order to solve this electric force, you need to draw the charges out. Draw a pair of force vectors between each charge. So if you only have two charges, you're going to have one set of vectors. Remember, they're going to be equal, but in opposite directions. If you have three charges, then you're going to have a pair of charges between each set. So you'll actually end up with three different pairs. So you'll have 6 forces total. So 6 force vectors on there. Because you have 3 different charges and a pair between each. So then you're going to calculate the force using the direction of the arrows of the vectors, not the charge. So you're going to decide, is it repulsive or attractive? And then based on if it's repulsive or attractive, that is the directional sign that you're going to give the force, not whether it's negative or positive. I'll do one. It'll make sense. And then add the forces using vector addition. So here's some pictures. Notice here we have 2 positive charges, but if we were looking at this in a straight line, we would say that this force is pointing in the negative direction and that force is pointing in the positive direction. That's what I'm talking about. Just because the charges are positive doesn't mean the forces are positive. The force needs to be based on direction. So give this a negative and that a positive. But they should be equal in magnitude because of Newton's third law. Equal but opposite direction. So here's another one. They're they're attractive. So this one ends up with a force towards the positive and the positive with the force towards the negative. Again, equal, but in opposite directions. This one actually ends up being negative because it's pointing left, and this one ends up being positive because it's pointing right. All right, and then we get one with 3. So we have a setup of 3. Now, this one is going to have a force vector here and a force vector here. So we can write that. This one will have a force vector here and a force vector here. So something like that. And this one, they've actually drawn it out for you. This is the force due to 1 on 3. And this is the force due to 2 on 3. So attractive and repulsive. So your total force is going to be probably in this direction. Because you have a force vector here and a force vector here. Don't worry about this part. That is the vector addition stuff, which we'll take care of without drawing. You just need to do like that much stuff. So here we go. We're going to do some examples. Aren't you excited?
Yeah.
You should be excited. We're going to do a charge at a coordinate point. We have 6 microcoulombs, which is a very common charge, micro, 10 to the negative 6. It's going to start at 0, 0. And then another charge is going to be negative 4 coulombs. It's going to be at negative 0.004 and 0.002. We're going to find the magnitude of the direction of that force. So this is an example at an angle, but it's only 2 charges. So it shouldn't be too terrible. The best way to start out is to draw it. So you have one charge here. This is our positive 6 charge, and it's microcoulombs, so we need to make sure we put that microcoulombs when we do the calculation. And then we have one at x is 0.004, y is 0.002, so we'll call it right there. And that is a negative 4 microcoulomb charge. So we're going to draw our force vectors. Positive, negative, so they're attractive. One like this, one like that. And we'll call this A and we'll call this B just to make things a little bit easier later. So we're going to find the force on each charge. The force on A, let's call the force on A. It's going to be equal to, and this is the force of A on B. Now, if we had C as well, it would be a force on A would be the force of A on B plus the force of A on C, or C on A. So straight up, pretty much. So this is an electric force, KQ over R squared. And this will be the charge of A and the charge of B. So we'll plug in 9 times 10 to the 9. We have 6 microcoulombs and 4 microcoulombs. Notice that I'm not putting whether it's negative or positive in because we already have direction. Now this one's that way and this one's that way. And then over them we need the distance, R squared, which because there's only 2 charges, all we really need is that total distance between. We can come up with angles in a little bit if we really want to. So this will be the distance formula, which is x is 0.004. And y is 0.002. That should be some sort of distance.
Oh, so it's just 0.004 squared plus 0.002 squared.
Wait, can't this question just be linear because it's just 2 atoms? Does that make any sense?
I still need to know the distance between them, though. I mean, yeah, we could move this down, but it's going to be a different distance. It's going to move in a... Not going to go straight down. It's going to go in a curve. Okay, so, oh, shoot. There we go. 4.47 times 10 to the negative 3. So we're going to replace that R. Don't forget to square it. That's a big problem that I see in people's work. All right, I made the number really big, but that's okay. That's what happens when you write your own problems. Force. Huge amount of force. Yes.
So when you put FA equals FAB,
the force on A is equivalent to all the forces acting on A, which in this case is force A on B. If I had a force up here of C, then we would have another force. Let's say that it's positive, then you have another force of C on A, so it would be the force of C on A as well as the force of B on A. I wrote it backwards. So the total force is going to be all the forces acting on.
so B is pointing in that direction because it's negative, or is it because it's negative that it points it in?
It's because it's negative, it's pointing towards the positive since they're attractive. This one is positive, this one's positive, so since it's positive, you're going to have a force pushing it away and a force pushing it up that way. Okay, and that's that negative part, that the charge determines the direction, but it isn't the direction. Okay, so how do you feel about this one? This one was simple.
Just
Yes.
for curiosity's sake, in this chapter, are we gonna just be talking about the charged particles, or are we gonna? Okay.
This is pretty much this chapter, this section is what we're focusing on.
So which one is the magnitude? Is the force?
Yes, this is the magnitude. This is the net force magnitude. Now your direction is going to be, the force on A is going to be whatever this is. And since we know this distance and, well, we know this distance, x, we know this distance, y, x, y, we know r you can do sine if you want to find that angle. It's going to be a little bit more difficult when we have two forces acting on it, which I'll show you how to do that. But for this one, it's actually just a triangle. So we know the distances, we know this angle, and that force is going to be directed along that angle as well. Not always, but in this one it is. So let's do that real quick. We'll do sine, which is opposite over hypotenuse. So theta equals sine inverse of Ry, which is 0.002, and our R, which is 4.47 times 10 to the negative 3. I got 26.6 degrees. Done. Yes?
Another thing, if you plug in U, how come U plus 6?
This one's 6. Up there, see the funny little MU hybrid micro? That means 10 to the negative 6.
Oh.
So I just replaced it. I didn't write the micro up here because I try to write it as simple as possible. And when I write it on the pictures, they get messy. Okay. Any other questions before we move to the next one? Again, this is the hardest stuff. So just let me know. We are going to do one extra practice worksheet on this stuff. I'm going to cover electric charges and electric fields tomorrow, and then we'll do a day of practice before we get into the test.
Wait, so the test is
Next Wednesday.
okay.
All right, now we're going to do charges on a straight line. I made it complicated, though, because I have 3 charges on a straight line. I'm really excited. All right, let me clear this board real quick. Mean?
That was very mean.
Well, I could just show you this one and then give it to you in the homework so you can figure it out yourself.
No thanks.
All right. See, that's what I thought. I thought maybe you'd like me to do one for you before you have to figure it out on your own.
If it's just on straight line, then
It shouldn't be too bad, right? Yeah.
Right.
Okay, so. Oh, I forgot to tell you, because it was charges on each one in the previous problem. The other charge would have been the same magnitude, but the opposite direction. Okay, so you would add 180 to it. But the force, the magnitude would be the same. I forgot to add that. That's simple. Okay, so we got a charge of, 6 microcoulombs at 0, 0. So this one's positive 6. And then we have another charge of negative 4 microcoulombs, and it is at 0.002. And this is negative 4. And then we have another one at negative 7. It helps if I read it correctly. One sec. There we go. Negative 6. Positive 6. Negative 4. And negative 7. Right? Okay, read that again. Make sure it works. Those are y's, not x's. That was my mistake. Okay, and what's the magnitude? And we want to find the magnitude on each charge. So we're going to end up with force of A, force of B, and force of C. So the first step, draw the forces between them. So we have 4 and 6, attractive or repulsive? Attractive. So you're going to have this one up here and this one down here. And I'm just going to call this A, B, and C to make this a little bit easier. So this is the force of A on B. This is the force of B on A. Then let's do B to C, attractive or repulsive? Attractive. So we have the force of C on B and the force of B on C. We're missing one more. A on C. Is it attractive or repulsive? Repulsive. So this one's going to push it here, so the force of C on A. And this one's going to push it down, so the force of A on C. Let's start with finding the force of A, just because it's there. The force of A is going to be the force of C on A plus the force of B on A. So see, that first statement is going to make more sense when you have more charges. And the last one is kind of like a duh, there's only one. All right, so we need to find the force of C on A first. The force of C on A is going to be 9 times 10 to the 9 times the charge of C, which is 7 times 10 to the negative 6. Oh, you know what? I forgot one more thing. The force of C on A is positive, and the force of B on A is negative. Put that negative in there. That's where you put the directions. So this is K, Q, and then Q, and then our distance. Now C to A is 0.002, 0.002, so it'll be 0.004 squared. See, these are some lengthy problems. All right, 9 to the 9, 7 to the negative 6, 4 to the negative 6, divided by done. A large number, because I did not check the numbers before I wrote them out. Next one we'll do is the force of B on A. 9 times 10 to the 9. Let's see, B is 6. So 6 times 10 to the negative 6. And 4 times 10 to the negative 6. And the distance between B and A is only 0.02 squared. There you go. That's nice. And you know, while we're at it, we have between C and A, B and A. Let's go C and B while we're standing here. Make it, because we'll use it in a little bit. So this would be 9 times 10 to the 9. The charge of C, the charge of B, and the distance between B and C. Thank you. Okay, so now we have the forces between each one. We have the black, we have green, and red. All right, that'll help us a little bit. Okay, so FA is equal to positive FCA minus FBA. So this will be CA 15750 minus BA. Let's do this. FA. Oops. So it says that the overall force is going to be pulling it down. Okay, then let's find the force on B. The force on B is going to be equal to the force on A of A on B, and that's up, minus the force of C on B, which is down, so that's why I made it negative. So FB, this is going to be force of A on B, 54,000, minus the force of C on B, which is this 94,500. Okay, and then we have one more to do. And that's F on C.
Yeah.
Oh, yeah, I typed in the wrong number. I had 154. Oh, that's better. Negative 40. Okay, so the down one wins is also going down. All right, F on C, we have positive FBC, negative FAC. BC is this one. AC is this one. What's up?
Nothing, it's just that they're all equal, the net force is 0.
All right, questions? You ready for 1 and 2 dimensions? Don't cry. It's okay. Okay. One more. Two dimensions. Yep, this one's 2 dimensions. I'm going to give myself a new one.
Wait, is this still recording?
It is still recording. Yes, it is.
Oh.
Somehow. It hasn't crashed yet. We will see. It crashed earlier in 4th period. I was very unhappy. It was such a good lesson.
That was like the Mona Lisa of your teaching career?
No. This is right here. Okay. We have a charge of positive 6 microcoulombs at the center. We have a charge of negative 4 microcoulombs up here at 0.002. And then we have a positive 7 charge sitting at 0.004 on the x-axis. So that's like here, positive 7. I'm going to label these A, B, and C just to make it easier for me. Now we have a set of forces between A and B. Are they attractive or repulsive? Attractive. So you're going to have one here, FB on A, one here, FA on B. All right. Now we have B to C, attractive or repulsive? Positive, positive. Repulsive. So this would be the F of C on B. And this will be F of B on C. And then we have between A and C, attractive or repulsive? Attractive. So this one is going to be the F of C on A, and this one is going to be the force of A on C. We do the same thing that we did in the last one, where we find the force of BA, CA, and BC. And then we'll deal with finding the force on each charge. So the force of A on C, 9 times 10 to the 9. The charge of A, which is 4 times 10 to the negative 6. There we go. And C is 7 times 10 to the negative 6 over its distance. Now, for some reason, I decided to work with the angled one first. Whatever. Creates a triangle. We have 0.02, 0.04, and we just need to figure out what our hypotenuse is. So, distance formula. And hopefully you guys have this written down because we just did this one. What was the R for this? Like that?
Yes.
Yes, that's it? Okay. That was completely from memory. I have no idea if I was right or not. Okay, so we're going to put that one in there. Okay, next one, the force of A on B. It doesn't matter what order you do these in, that's just what I was thinking of next. 9. A is 4. B is 6. And the distance between them is 0.002 squared. And the last one, between B and C, 9 times 10 to the 9. B is 6 times 10 to the negative 6. C is 7 times 10 to the negative 6. And this is 0.004 squared. Okay, so now let's find the force on each one of these and look at its direction. We're going to start with the force on B first because it's the easiest one, and then I'll show you why the other two are a little bit more difficult. Okay, the force on B is going to be equal to the force on, this one's still going to be, not so fun. Okay, it's the force of FAB straight upwards. And then the force of CB to the left. So we're going to end up with some force here, force B. This is where your vector stuff comes in. It's kind of nice. So FB is equal to FAB minus FCB to find the magnitude. You do your vector equation. And we get F582 newtons, and the directional equation, tangent inverse of y over x And since x is negative, you're going to add 180 to it as your adjuster. And that will give us 114 degrees, which is more than 90 but less than 180, so that seems about right. Should be okay. Okay, so now we need to do this stuff, which is not so fun, but that's okay. These things happen. What we do need to know is these angles. That will help us. So using our SOHCAHTOA stuff, we need to find this angle and this angle, which I'll just call phi for now. So sine inverse for this, opposite over hypotenuse. And I get 63.5. And then I'm going to cheat and just go 90 minus 63.5. Give me 26.5. So this is 63.5. And this one is 26.5 degrees. Okay, so that's going to be helpful. We'll put in the proper angles here in a little bit. Actually, we should probably do that right now since I got to do them anyways. So proper angle, or standard angle, as I have been schooled by the calculus teacher. If this one is 26.5, what is this angle? This is phi. 180. 80 minus 26.5. This is 153.5. This angle, what is that? Will be 360. Nope. 270 plus 63.5. Give me 333.5. Are you guys okay with those proper angles?
Oh, yeah, I see.
Okay. And then this one's just straight down, and this one's to the right, so we could just use I-hats and J-hats for that. Let's do f of a first. F of a is made up of FCA, and here's the nasty vector part. Sorry, guys, this is how it goes. Cosine 333.5. That will give you your I-hat plus FCA sine 335 or 33.5 J-hat plus, so that takes care of this vector in both its x and y components. And then we've got this straight down FBA, and since it's straight down, minus FBA, BA, and that's in the y direction, J hat. I'm going to clean this up a little bit first. This is going to be 0.895. And this one is going to be negative 0.446. That'll just make it a little bit easier. Let me write it down next. So we have FA is going to be FCA 12612 times 0.895 I-hat plus 12612 times negative 0.446 J-hat minus FBA 5400 J-hat. Add up your J-hats, then your I-hats. Okay, those are your components for FA. Find the magnitude and the direction. I don't really want to write it all out, so I'm just going to write the answer. Because I'm lazy. Don't be like me. And it's 60684 newtons for the magnitude, tangent inverse of y over x plus 360. 280 degrees. It's like 281, but and now the last one, and I'm going to try to do it in 5 minutes. So. Same setup as this one though, so FC, it's going to be f of A on C cosine, what's its angle, 153.5, and that's an I hat, plus FA on C sine 153.5 J hat. And then this other one here is FBC, and it's pointing to the right, so it's positive FBC I hat. Because it's X direction I hat, and it's pointing to the right, so it's positive. Let's simplify these a little bit so it looks nicer when we put them in our calculator. Cosine 153.5 is negative 0.895. And then this one, sine, have a feeling what that is. Yep. 0.446. So those numbers pop up again, which makes sense. And then FC, our FA on C, this again, 12612, 0.895, plus this again, 12612 times 0.446. Plus our BC now is 23625 I hat. This is an I hat, and that's a J hat. Now I already did these calculations on this one, so this is the same number here, just going to be negative. So this will be negative 11287 I hat. And then this one over here is going to be positive 59625 J hat plus 23625 I hat. Combined I hats and J hats. I told you this is next. So we have an FC of 12338 I hat plus 59625 J hat. Magnitude 60888.
Good afternoon, parents. Please listen up your afternoon announcements. The ASVAB test is being offered again here at Palm Bay Magnet High on February 25th. Sign up in the guidance department before or after school.
All right, and there's your answer. On your homework tonight,
Just a reminder that we have tutoring after school.
I want, when it says find the charge on F, on like A, I want you to find the charges on all the charges, just so you know.
To get tutoring today. Students, just a reminder
And I definitely went the wrong direction.